So we will move ahead with the demonstration session next. Over to you, Nikhil.
Yes, ma'am. So, based on this Arnab sir session, I will going to demonstrate some few of the cases, which is also based on a droplet and bubble. So, we're going to see the same two-phase flow based on VOF method. But yesterday, what we have seen, it was based on two continuous fluid interacting with each other, like a wave and dam break case. But in the today's case, uh, I will going to cover these two cases, which is bubble rising using VOF and the droplet case. So we'll see one by one all these two cases. So coming to this bubble rising case, so in this, uh, it is something like air is trapped inside the water column. So this is the geometry of that test case, and we will going to uh, trace the interface of the air bubble, which is trapped inside the continuous water phase using VF method, and we'll going to see both the cases with static mesh and with the dynamic mesh. That is the adaptive mesh refinement. So these are the again same governing equation which I have covered it yesterday. So again, as a recap, so the first one is the uh, continuity equation. Second equation is the momentum equation, in which gravity and surface tension term will act as a source term. And to capture the interface, a phase equation, uh, it will going to solve. So coming to these boundary conditions, so this is our geometry, and this three wall has been given the no slip boundary condition. That means the velocity on all these three wall is zero. And this is the pressure outlet condition. That means the atmospheric condition, which means the bubble will leave this flow domain from this patch. That we're going to see how it will going to leave. And on this bubble, the gravity and the buoyancy force will going to add. And because we are capturing the interface, so we can easily calculate the buoyancy force based on the deformity in the shape. So coming to the test case, so this kind of test case we can easily modify using the same dam break case. And so let me show you how to modify it. So other things will be same, like inside the zero folder, there will be three files, pressure, velocity, and alpha phase one. So if you see alpha phase one, yeah. So here we are defining on all the walls as zero gradient. That means with calculation, it will going to uh, calculate the value of alpha on these walls. And we are solving for the 2D case. That means front and back will be the empty. That means it will not going to solve for the front and back cases or patches. Similarly, coming to pressure and velocity. So as I have said that uh, no slip boundary condition has been implemented on the wall. So instead of so both the ways we can define no slip boundary condition. Either we can define the velocity, all three velocity as zero, or we can simply write as no slip. And again, the top patch has given the boundary condition of pressure inlet outlet velocity. Now, similar to velocity, pressure has given wherever the velocity is fixed value, the pressure will be the zero gradient. So that's why on all the walls, zero gradient boundary condition is implemented for the pressure. Now, uh, the mesh will be the mesh will become the very simple. Using the block mesh will define the mesh, and it will be a simply a rectangular box. So that also I will show. Yeah. So it is simply a rectangular box. In these are the vertices mentioned here. And instead of dividing the whole geometry into various blocks, we can define it as a single box, single block. where the X, Y is divided into these many subsections. So first we'll see the mesh, and then we'll see how to initialize it for the bubble case. So I will go to that location. I'm using OpenFOAM 2412 for running this demonstrative case. So first, I will make the mesh. Using block mesh command. Then we can check it using check mesh. So our total number of elements are 12,800. So if you want to visualize now, we'll simply open the para view to visualize our basic mesh. So this is our computational domain. And if I select surface with edges, so you can see the mesh given for this computational domain, and it is very fine. So in case of this surface or interface capturing application, it is advised to give a very fine mesh to properly capture the interface. If you are not changing the mesh using adaptive mesh refinement or any other technique. So because our mesh is static, so everywhere we have defined this fine mesh. So now coming to the initialization. So again, the initialization will be done using set field dict. Yeah. So the default value, because it's air trapped inside the water column. So everywhere we'll first define the water as phase 1, means the alpha value of 1. And to define the bubble as initial condition, we'll define it something like this. We'll define it as the 3D cylinder. Anyhow, the front and back, it will not going to solve. So it will appear as a 2D circle. So we'll define the point that it means the center point of the circle in on both the planes and the radius. And based on these points and radius, we'll define our volume scalar field alpha value of 0. So alpha value of 0 will initialize the bubble. So we'll see. I should create a new alpha file. Yeah. So using set field. Yeah. So now you can see it is saying that on these points with this radius, it has initialized alpha phase of 0. And if we'll see this alpha file also, we can compare both alpha original file and the initialized file. So in alpha phase 0, the internal field is showing the 0 value, means everywhere in the domain only there is or alpha field is there. But after initialization, it has initialized some values of 0 and 1. So wherever we have defined the cylinder to cell value of 0, it will take 0 value there. Otherwise, everywhere inside the domain, it will take the alpha value of 1. So now if we'll visualize this, So we'll simply drop down this one and we'll click on alpha phase 1. So now we can see uh, blue patch is appearing here. So this blue patch is nothing but the alpha phase of 0, which we are referring it as the air bubble, and this red phase is the water column. So to see the uh, bubble rising dynamics, uh, I am using the solver called as Interform, which is well known for tracking the interfaces, which I have showed yesterday also. I will simply run this Interform solver. So as it is a 2D geometry only, it will not take much time to complete the simulation also. Till now, if you'll see, it has run till 0.82 seconds. And it has started saving the files also. So it's better to visualize. So we'll first refresh it so that all the time step will appear on the para view. Now, if you'll see, 111 time steps it is showing, which are appeared. We'll simply switch on the play and we can see how the bubble is deforming inside the water column. So anyhow, this is taking time to show. So the animation I have made here. So you can visualize this, how the bubble will going to deform inside the water column and how it will going to leave the fluid domain from the top patch. Yeah. So in this, you can easily track the interface of the bubble, and using Paraview or using some open form utility, you can also calculate the volume of the whole bubble. So this was the first case. So after this, if some questions are there, we can take, or ma'am, should we take questions now or towards the end?
Maybe we can take at the end of both.
Okay, fine. So similar to this rising bubble case, as in the previous section, we have seen some droplet cases also, which Arnab sir has demonstrated. So we can simply reverse the initialization. We can see that. So instead of giving the default value of 1, we can give the default value of 0 and initialize the droplet. So again, in the same set field. So earlier, if I'll compare with the bubble rising case, here I have initialized the default value of alpha 1. That means everywhere it will take the alpha value of 1. Means for this case, we are considering it as water. Now, in case of droplet, when we want to see the droplet impact on the solid surface, that in that case will initialize the default value as 0. Means everywhere it will take default value of 0. That means it will take it as a air domain. And to initialize the water column, water droplet, again we have to define the 2 points radius and we'll initialize it with the alpha value of 1. Uh, Remaining things will be the same, means how we are giving the boundary condition for the bubble rising case, and the properties will be also same. Only now instead of bubble, we are considering it as a droplet. So I will simply change the folder. Yeah. Now this will also consist of the same block mesh. Check mesh and set fields. Yeah. So now you can see it has initialized the droplet at these two using these 2 points with radius of 0.25. Now, if we want to visualize this, so this is our fluid domain with the mesh refinement. And if you want to see the initialized field, then again we have to select this alpha. So now you can see this red zone is denoting the water droplet, and this is the air domain. So now if I will start uh, solving this whole fluid domain, now because of the density and gravity, the heavier fluid will slowly come down and impact the bottom surface. So that we'll see. So again, as this is the interface tracking case, again we'll use the interform as a solver. And the properties of the fluid, it is nothing like it is defined alpha dot water, so you cannot vary the density of or kinematic viscosity. It depends on the application that or what kind of fluid you want to take. So as this is a 2D case, it will also not take much time to solve the whole fluid domain, and we can see the nice animation out of it. So by the time it is solving, this is the computational domain for the droplet case. Now, instead of buoyancy force, which I have showed earlier for the bubble rising case, now for the droplet case, the drag force will come into existence. And this also we can calculate as the bubble will come down, its shape will deform. And based on its shape, we can simply calculate the drag force. So this is how the bubble will fall and hit the bottom surface. We can stop in between and see if it is taking too much time. So we can simply select alpha water. So the animation that I showed was having some different viscosity and density. That also I will I can show what the velocity, sorry, not velocity, density and viscosity I have taken for solving this case. And in this case, which I am showing it right now, uh, here I have taken the density and viscosity of water and air. Yeah, so this is how it will going to impact and the splashing effect. Now, in the droplet case itself, if you want to simulate the hydrophobic or hydrophilic nature or as a property of the drop, so that also we can define. Yeah. So here I have defined the water phase as Newtonian with a kinematic viscosity and density, and air is also defined as Newtonian fluid with kinematic viscosity and density of this much. And this is the sigma value. So this also you can vary. So suppose instead of this, if I'll take these value, which is uh, the kinematic viscosity of 0.01, that means it is a too much viscous fluid. So we can see how it will going to affect the drop dynamics. And if we'll increase the sigma, that is the surface tension, so it is means compared to water, this the sigma is too high. So we can compare based on that. So I will delete this one. Yeah. So for this case, I have only changed the property of the fluid. So no need to initialize it again and again. Directly I can use the interform command to simulate for this case. But whenever you are changing the mesh or geometry, not geometry, only the mesh. So currently I'm using the mesh size, total mesh element of 12,800. But if you are refining it further, after refinement of the mesh, again you have to do the set fielding. You have to run the command of set field to initialize it again. Yeah. So you can see we have simply changed the properties of the fluid, of both the fluids, and how it will going to behave, we can visualize from here. So earlier I have taken the properties of fluid of water and air. So now some random values I have taken. So now you can see while the drop coming down the whole domain, the shape is not varying that much. It is uniformly distributing in both the direction. So the animation of the same uh, simulation I have showed it in the slides. So I've stopped it in between. So that's why it has simulated till this point only. If you'll simulate it further for the time step, you can see it will come down and hit the solid wall. Now both the cases which I've showed, that is the bubble rising and droplet case, here our mesh is not changing. And also to capture the interface, we are requiring this fine grid all over the domain, which is not required sometimes because we are only capturing the interface. But what about this portion? Here, this much refinement is not required, which will anyhow increasing the computational time. So to counter this, we can use adaptive mesh refinement. So what it will do, we can make a very coarse grid, and it will only going to refine where we want to capture the interface. So that case also we'll see, and how it will speed up our simulation. So this is the bubble rising case with AMR. AMR is nothing but adaptive mesh refinement. So again, the boundary conditions and everything will be the same. What will going to change, that I will show. Now, in the constant folder, other than these three files, that is G, transport properties, and turbulence properties, one more file is appearing, that is dynamic mesh file. So whenever you want to do the dynamic meshing, dynamic mesh refinement, or that adaptive mesh refinement, it will not you cannot use adaptive mesh refinement when you don't have any scalar properties or scalar as a variable, because if it want to trace or any interface or any other dynamics, it requires some scalar properties. But for this VOF method, we already have one scalar field, that is the alpha scalar field. So based on this field, it will going to trace the interface, or it will going to refine the mesh. So in this dynamic mesh dict file, we'll first define what is our field. So we are giving the alpha field. Now we have to define up to what level it will going to refine. So the lower limit and upper limit we have to define. And in between this two limit, it will capture the interface of the either the droplet or the bubble. Now maximum cell we have to define, that this much cell is required to capture the whole interface. We can increase or decrease based on our requirement also. So after defining this, I can show the basic mesh, how coarse it is. So I will delete this file and I will make a new alpha file. So if I'll open it, you can see it is not initialized yet with an internal field of 0. So first we'll create the mesh. So now if I'll compare both the refined means the earlier bubble rising block mesh dict file and this block mesh dict file, so you can clearly see how coarse this block meshing I am giving. Yeah. So this was the earlier file where we are refining all over the domain. So in this, the x length or the width, we are dividing it into 80 subdomains. We are dividing into 160 subparts. Now coming to the adaptive mesh refinement, I'm giving only 10 and 20 in x and y direction, keeping all the mesh elements as uniform. So now first we'll see our block mesh. So now compared to 12,000 cell in the fluid domain, now it is only 200 cell. So I was showing the current block mesh with adaptive mesh refinement. So we can see earlier our mesh size was 12,800. Now it is only 200. So we can see how coarse it is. And we'll also visualize how the interface is coming after initialization. Yeah. So you can see compared to, it's better to open both. So this was the earlier mesh domain in which this much refinement we have given to capture the interface. But for the adaptive mesh refinement, this much coarse mesh we are giving. So the idea is we're not going to refine the whole domain. We're only going to refine the interface, which will help in speeding up the simulation also. And the maximum refinement near to the interface we are giving as 40,000 mesh, total mesh. So now we'll go for initialization. So again, for the initialization, the same file I'm going to use. So it's a bubble rising case. So everywhere default value is 1, and only for initializing the bubble, I'm giving the alpha value of 0. So I will run this set field command. Yeah. So now it has successfully initialized. Now if we'll visualize, now if we can see how means it's just an initialization. So how badly it has captured the bubble. So it is because we are not giving that much refinement to resolve the interface. So now coming to solving this using adaptive mesh refinement. So the adaptive dynamic mesh dig file I have already shown that how it will going to resolve the interface based on this upper and lower limit and the maximum cell size of 40,000 we are giving to capture the interface. So now if I'll run the interform, we can see with each iteration it is showing that how much cell it has refined. Yeah. So after the time step of nearly 0.6 second, it has refined almost 2000 cells. And as the time approaches, it will keep on showing that how much cell it is refining. So it has already reached the time step of 1.5 second. So we'll stop in between and we'll visualize it. So now you can see as the time uh, with time, how it is nicely capturing the interface, and the same what we have seen earlier, how the bubble will behave inside the fluid domain. The same behavior we can see it here with the coarse mesh with adaptive mesh refinement. And to further refinement, you can increase the maximum cell size and the upper and lower limit. So now you can see compared to the initialization, how well it is capturing the interface. So anyhow, it will take much more time to escape this fluid domain. So it's better to stop, and I will show how it is refining the mesh. It's better to switch this on. Yeah. So now you can, it's better to switch off. So the mesh visualization will be easy. So now, if you'll see how the mesh will start to refine near to the interface, and slowly it will going to change. So because of this, means the whole domain is having very coarse mesh. Only it is refining near to the interface of the bubble. So what this, if I impose the phase field also, we can nicely visualize with respect to the interface how with each iteration or with each time step how it is refining the mesh around it. So now if I want to further increase or sharpen the interface, I will increase the upper limit and lower down the lower limit, and I will increase this to 60,000. So from here I will delete all the time step. Now here also I'm not changing the mesh, means the block mesh, the steady mesh. So I don't have to initialize it again and again. I'm only changing the dynamic mesh dict file. So if here if you'll see, I'm not changing the mesh. Only we are changing the dynamic mesh file. So now instead of the lower limit of 0.01, now I'm defining the lower limit of 0.001 and upper limit of 0.95 and the maximum cell of 60,000. Now based on this, it will again increase the sharpness of the interface. So again, I will run interform. I can stop the simulation after 1.5 seconds. Yeah, it's better to stop and we can visualize it. Yeah. So you can see at the time step of 0, and there is no refinement around the bubble interface. But just after this, it has started refining. So it depends on application to application and that how well you want to capture the interface. And based on that, you can manipulate the upper and lower limit and maximum cell value. So at the time step of 1.67, it has reached this much height. So if we'll run it further, we can see how it will move out of this domain. So this was all about capturing the bubble interface and the droplet using both static mesh and adaptive mesh refinement. Now, if you have some question, you can ask. Yeah, if you have any question, you can unmute it and
Sir, if we want to rotate the whole domain, is that possible?
whole domain like
Like make it as a rotating box.
rotating box. Yes, 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 you can do it. So it's better to explore the dynamic mesh dict file. So in my dynamic mesh dict, in this, I have shown how to refine the mesh based on the alpha value. So in the dynamic mesh dict file, there are various options. Means you are saying that with respect to simulation, how it will start rotating, right?
Y-axis. If I
Huh.
want to rotate around Y-axis, suppose.
So with simulation, it should rotate, or how?
This is but just I have idea. Suppose if this
You can
domain
rotate it,
is.
yes. Using dynamic mesh file, you can rotate it, yes.
So what should I change? Can you please illustrate
Okay,
that?
so that's what I was asking. Whether you want to simply rotate the file and see the dynamics of flow, then you can simply change the block mesh file. Okay, or using this, if you don't want to change the dynamic mesh file, you can use transform points command.
Is there any tutorial about this rotating domain, suppose?
Let me check. If it will be there, we'll post it. Okay. And regarding which case I have used for the today's tutorial or demo session, you can refer this test case, which is given in the research migration project. So if you'll see, if you go to FOSSEE site, there is completed research migration option is given. You can refer this one under research migration project. You can refer this 45th test case. So in this, the whole test case is given with the explanation how to set up the test case for this bubble rising case. Plaban sir, you are asking to explain AMR part again. So should I have to explain the whole thing or some specific portion you want to see?
From general block mesh to
Oh,
adaptive.
from general block mesh to, okay. So this is our block mesh file, starting with defining the vertices. So now it is a single rectangular box, so only one block will be there. And this coarsity of the mesh will be dependent on you. So I've given a very coarse geometry of meshing with 10 elements in the x direction, 20 elements in the y direction. So that's why this much coarse mesh we are getting. I'll switch off this field. So based on this block mesh file, we are only generating 200 cells in the entire flow domain. But if you want to capture the interface, we are using this adaptive mesh refinement file. And as I've said, it will going to read the scalar field. So that's why we are giving here the field of alpha. But if you have some other scalar field, in the yesterday session, Ivan was showing how to add the scalar field. So even that scalar field you can use for adaptive mesh refinement. Now we have to define how well we have to capture the interface. So that will be dependent on the upper and lower limit. So you can further decrease the lower limit because anyhow zero it will not going to read. So near to zero value you can give, and upper limit you can give as 0.999 something near to 1. So as you go closer to the actual value of 0 and 1, it will going to capture the domain with that much sharpness. And what will be the maximum cell it will going to generate around the interface, that you have to define it here. Is that fine, sir? Okay, we'll share the dynamic mesh dict file.
I have one question.
Yes.
That is, while doing with the AMR, the
Okay.
initial part of the transient simulation, it is very coarse, right?
Yes, yes.
So is it the means common? Is it common to
Yeah, it is
all?
common. Yes.
Okay, okay. Thank you.
Hi Nikhil, are you there?
Yes, yes.
Exactly, I asked the question regarding the there is 2 points you have mentioned about 0.5, 0.5 and 10 and
Okay,
another
okay,
one
okay.
is minus 10. What is that 10 and minus 10 it is pointing out?
Okay,
It is
okay.
the
So see, we are it's in the 3D, it's a 3D point, right? But we have to solve it in a 2D. Okay, so if I
right.
show you uh, the computational domain, so thickness I have given of 0.1.
Can you share the screen, please?
Oh, sorry. Now if you'll see in the block mesh, I have given the thickness in the Z direction of 0.1 only. Okay. So to define the field, what I have done, I have simply taken it as a cylindrical, initialized it as cylinder, and simply passed on both the side of the domain, or simply allow it to exit on the both side of the domain. So anyhow, we are not solving in the Z direction, so it won't matter unless it is more than the thickness of the geometry. So you can give 2 also, it won't matter.
Okay, that's my
Okay.
point.
Yeah.
Okay, thank you.
Yeah. Okay.